Great, thank you everyone. Give me a moment while we switch the technology. Hopefully this will go smoothly. It's a pleasure to see you all, and it was nice that we got to have that panel discussion earlier. Thank you, Jing, for moderating. That was an engaging discussion. I know we're right after lunch, so hopefully you're not too sleepy. So I'm going to be talking about some emerging patterns in AI for science. So it is true that my background is in particle physics, and this diagram here is a visualization of the kind of data that we collect at the Large Hadron Collider. And I will give some examples that come from physics, but I promise you don't really need to know any physics, hopefully, to follow my higher level point. So I'm going to start off with something that I think everybody knows is that AI and machine learning are exploding across the different sciences. Here's just a figure of what that looks like in materials science, chemistry, and physics. And you can see this kind of hockey stick takeoff. So these fields have been using different types of machine learning in different ways for decades, but if you think of roughly 2012 as when kind of the ImageNet moment, when deep learning really started to take off, it takes a little bit of time for people to figure out how to leverage that, and then you can see something kind of emerging, and that's where it takes off shortly thereafter. So recognizing this, there have been communities that are starting to develop. So I'm pleased to be one of the kind of co-founders and co-organizers of this workshop called Machine Learning and the Physical Sciences that's at NeurIPS this year. I think it's our 8th year that we've done it. There's also a community called AI for Science that's had a series of workshops at the various machine learning. And then of course, there's a huge number of more specialized conferences and workshops that are popping up all over the place. And so those kinds of workshops are usually focused on a particular domain and the kinds of questions that you see there. But there have also been some efforts to try to ask a little bit of a meta question about like what's going on here. Is this an emerging field? How should we think about all of this activity? So one such conversation was held in Germany and Dagstuhl. We had a Dagstuhl workshop organized by the University of Cambridge, Tübingen, when I was kind of transitioning from NYU to Wisconsin. And it was a nice, thoughtful group. And in that conversation, we were thinking about, okay, well, what kind of patterns are we seeing it? But the way that it was framed there is well, this was the kind of outcome of that workshop is, for instance, one theme that you see is how do we incorporate domain knowledge, like our scientific knowledge, into the machine learning or AI approaches. So that was a whole lot of activity in that space. There are various things about interpretability, the issues of how do you take advantage of machine learning and AI in the context of simulations, or how do you relate it to causality? And this was a very fascinating workshop, and there's a link that's too small to read on the side for our the findings of that, but. It was a useful discussion, but it's one lens at which to look at all of the activity. But in this talk, I'm going to kind of talk about a different way of thinking about the different activities that are going on and these different patterns that are emerging. So I'm going to get to that in a second. But before I do that, I also want to just kind of introduce this concept and ask ourselves this question of. When you talk about what's happening in machine learning, especially to a lot of computer scientists, oftentimes it's like, oh, these are applications of machine learning to the sciences, with this kind of idea that like we've got it all figured out. And so when you think about research broadly, there's this kind of two-dimensional landscape that you can think about the kinds of research. So on one axis you have basically, is it practically useful? And another axis is there's some kind of quest for fundamental understanding. And so you have these sort of different quadrants. And so oftentimes when people use the word applied research, they're thinking, okay, it's something that's practically useful, but it's not necessarily advancing fundamental understanding. And so that framing can be used when you're talking about, say, physics. There's like applied physics. You're not trying to understand the fundamentals of the universe. You're trying to do something useful with it. But here I want to think about the context of machine learning and AI itself. Okay, so are you trying to push forward the foundations of machine learning and AI and our understanding of those things, or are you just applying AI to a problem? So that's the way that I'm thinking, I'm discussing here. What I mean by the fundamental understanding axis is really about understanding AI. So our computer scientists maybe would be more in the, say, pure basic research direction where you're thinking about, computational complexity or the underlying architectures and attention mechanisms and things like this. And so this framing is, I think, a problem oftentimes because it will, for various reasons. One is it makes it difficult to get computer scientists to engage in a lot of interesting research because it just seems like it's applied. I'm not gonna learn anything. I'm not gonna be able to, it's not intellectually interesting for me as a methodologist. And so I'm, really big on this idea of use-inspired research. And this framing is, I think, really important. And it builds on the observation that foundational advances, in this case in machine learning and AI, are often inspired by the context and peculiarities of specific applied problem settings. So there is maybe an applied problem setting, but you don't have a solution for that problem, or at least not a satisfying one. And so when you're trying to understand it, you have to figure out how to articulate why the existing candidate solutions are not good solutions for your problem, and what are the particularities that you have to deal with that need to be solved. And then that often then spurs foundational advances. And so there's these kind of phrases like necessity is the mother of invention. I also like this one that reality is stranger than fiction. If you're just a kind of a theorist sitting in your corner trying to think of like what's the next interesting problem to solve, you have to use your imagination to come up with what's the next interesting thing. But reality is full of very challenging problems that maybe you would have never thought of. So these kinds of things are at the back of my mind and all of the kind of research that we're doing in AI for science. This figure is just to kind of point out that I think it's also often the case that there aren't off-the-shelf solutions that are going to solve the problems that we see in science. Okay, so with that in mind, what are some examples? So in the context of, for instance, particle physics and astrophysics, you have complicated detectors or sensor arrays and things like that that are not like a nicely organized grid of pixels for a camera. And early on in deep learning, convolutional neural networks were like one of the major architectures that everyone used because they were very effective in dealing with images. And so there was a period where everyone tried to figure out how to reformat their data so it looked like an image so they could stick it into a convolutional neural network, which is kind of like a funny way to do things. And so if you turn it around, you're saying, okay, well, actually, you don't have a good architecture for dealing with my type of data. And so these are early examples where use-inspired research was really pushing the envelope in terms of what's called geometric deep learning, graph neural networks, and things like what we see with transformer architectures today. More generally, I think there was this kind of, these are slides that I would show along the last several years of doing this kind of stuff, and this observation that I like a lot, that if you're either you're a physicist or a biologist or a linguist or something, you have some domain knowledge, and that domain knowledge you have an idea of like how the data would be generated. And if you have some insight into that data generating process, then it's just very natural that you would like to have a machine learning architecture that somehow mirrors that and somehow like reflects that. And so in machine learning language, that's often referred to as inductive bias. And so there are some examples here of molecules. You have an idea of what molecules look like, so you would like a network that kind of looks like a graph type structure. Even for sentences, there's ideas of like how you might parse a sentence or something. And so again, these are kind of older, a few years old. That paper is from 2018, not 1918, feels like it sometimes with the rate that things are moving. But there was a period in the kind of AI for science where this was like, it still is, but was like one of the main topics of conversation is how do we incorporate this type of domain knowledge into the architectures and the inductive biases, and is that helpful or not? And so there are different kinds of themes that you would see at that time, like notions of compositionality, relationships between objects. Sometimes if you know that you have a problem that has a certain symmetry in it, how do you incorporate that symmetry? Ideas of causality, and scale separation. And over the years, we figured out basically how to incorporate all of these kinds of ideas into architectures of neural networks. And so that's, that's been rewarding. And, so that there was that period. But kind of my most recent thinking about how to try to help organize or provide some kind of taxonomy about all of the activity in AI for science is kind of the following, and that's kind of what the title of the talk is about, is this next stage. Actually, I kind of continue building up to it actually. So if we go back to that use-inspired research framing, I said that there's this kind of particular context or peculiarity that is what, that makes these problems interesting and drives methodological advances. So what are the kinds of things that, say, you see in the physical sciences that are pushing things forward? And it's not everywhere, but pretty commonly one of the themes is that we have simulators. So we have some mechanism in mind, which are the kinds of things that, like a physical law or something, and we can put them into some computer code. And if you think about science, it's replete with high fidelity simulations. So we have simulators for particle physics, we have simulations for how neurons in the brain move, how proteins fold, how air flows around an airplane wing, how gravitational waves are formed, how the universe at the largest scales evolves. And theory these days is much less commonly like an equation on a blackboard, and is more and more, the modern manifestation of theories is often in computer code, and it often involves people modeling different kinds of phenomena happening at different scales that you compose together into something that's, really requires several different types of domain expertise, but the simulations can kind of piece them together in some kind of multi-scale hierarchical type of model. And so I just start with this statement that the forefront of scientific knowledge is often encapsulated in some simulators. And then when you think about what are they kind of conceptually, they generate data. So a computer scientist might say they're generative models, and that's true, but they're much more than just normal, they're much more than like a random black box neural network generative model, because they have that mechanism inside, they're causal. So you can use them to extrapolate to systems that you've never ever seen before, or imagine what happens if you did a certain intervention, and you can simulate those scenarios, which a typical black box generative model can't do. The other thing that's important is that it couples very well to all of the investments that we've seen in terms of scientific computing, programming languages, cyber infrastructure, all of these things. So that framing around simulators is, I think, a good way to kind of acknowledge and leverage all of those investments. But unfortunately, and this is somewhat ironic, is that even though those simulators might be very high fidelity and be able to produce data that looks a lot like the real world data, they're hard to work with. And in particular, they're difficult to work with when you want to do statistical inference, experimental design, or somehow incorporate them in terms of a decision-making framework. And it's a bit ironic that that's the case, and I'll try to elaborate a little bit more about why that's the case. Excuse me. But let's just take it for granted now. But so we would like to somehow be able to leverage these simulators to do those things, because they're at the heart of all sorts of things that we do when we do science. This kind of somewhat ironic situation was acknowledged by Paul Dirac, famous physicist associated with the development of quantum mechanics about 100 years ago. And he's saying that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and that the difficulty is only in that the exact application of these laws leads to equations much too complicated to be soluble. So there's this piece where sometimes you might know what the mechanism is, or at least believe in the mechanism. That's not what you're debating, but the computational consequences of that, or how you can work with it, are still very difficult to work with. So coming from the Midwest, now that I'm in Madison, I have to include cows in my talks, and trained as a physicist, we're often trained as this idea of a spherical cow model. So you get asked for a problem like, what's the chance that lightning hits a cow on some day? The first approximation you do is that the cow is a sphere, and then you do some calculations. And while that is kind of laughable, it is, it has done us well. I mean, like that, those kinds of simplifying assumptions and abstractions are very useful, but they have their limitations, right? And so I think one of the things that we're seeing with machine learning and AI right now is that the ability to make basically something like this, which is like a much higher fidelity approximation of what that cow looks like, but it's often more difficult to reason about. So the advantages of the sphere, it has very few parameters, and you can communicate it and you can characterize it very easily, while something more complicated like a cow is difficult to reason about. However, it is much higher fidelity, and now with neural networks and things, they often very fast from a computational point of view. So here's an example of one of the ways that manifests itself as AI and machine learning as an emulator. So in this animation on the left is going to be a physical simulation that's like moving a bunch of little objects around according to Newton's laws. And the left is going to be a neural network which has essentially learned what that is and is going to emulate that. And so when you see the kind of phenomena that you can describe, it gets to be quite complicated and look very realistic. And so these types of these types of emulators can be very, very fast and have a lot of nice properties like being differentiable and things, which allows them to be used in settings where the normal simulation, maybe you wouldn't have been able to use that. So this is there are different ways that people have talked about what's happening here, and one of them that I like quite a bit is actually comes from Microsoft Research. This is Chris Bishop, and they've kind of building on this idea of I don't know if you're familiar with this book and this idea of the fourth paradigm, but this was going back to maybe like 1990 roughly, or 2000 maybe, that when people were talking about if you look back at the history of science, that there's like an early on empirical kind of paradigm, and then there was a more theoretical paradigm, thinking kind of like Newton and Galileo or something like that. Then it moved to a more computational paradigm, and then what was happening, this is around the time of big data as a buzzword, was that, okay, you have a lot of data, you have a lot of computing, and that this kind of data-driven discovery or data-intensive science and these kinds of terms were floating around, and that was very much tied with this fourth paradigm. The thing that was unsatisfying about that paradigm is it tended to forget about the important role of theory. It was kind of like, you can forget about all of your domain expertise. We're just going to have a bunch of data and a bunch of computing, and everybody's out of business, and we don't need you. And there were even papers like the end of theory, like articles, the end of theory and things during that time. And so this fifth paradigm is in some sense is recognizing the role of theory. So the role of theory is basically, though, manifest in these simulators. So you have underlying physical laws, underlying mechanisms, and so you that's useful, but it was difficult to work with them before, so you could maybe produce a bunch of synthetic data. But what's happening is it seems like AI and ML is like kind of is providing these capabilities that allow us to kind of put them together and make them operational and do something useful with them in a way that we didn't know how to do before. So this is, I think, still incredibly compelling. It's not quite as hypey sounding as like AI is just going to automate all science and something like that, but for me, it's in a much more credible and specific way where AI and machine learning is providing capabilities that's doing something that I think most people agree is useful and something that we didn't really know how to do before. So there are various examples. This is Max Welling. He used to be running the Microsoft Research Lab in Amsterdam. Now he has a startup trying to design materials for doing carbon sequestration and things like that. But at this time, he's talking about numerical weather prediction, and those are like big supercomputing type calculations that take a very, very long time. And now there are AI emulators that have basically learned what's going on and can run those simulations 10,000 times faster, and that's leading to really a revolution in what's going on in numerical weather forecasting. And there's a lot of promise that something like that can also be useful for longer time horizons for things like climate. And so that's an example. Another example where this idea of emulators is pretty interesting is in the context of fusion. So there was a partnership between deep learning and EPFL in Switzerland where they had basically it's a tokamak. It's like a big donut. There's a plasma inside of there. You're trying to make very high temperature plasmas to extract power, and The problem is those plasmas are unstable, and so you need to control them with a bunch of electric fields and magnetic fields and things like that, and that's a classical engineering control problem. And so they use classical engineering approaches to do that, and those are very advanced techniques that have been developed over many years. But at the same time, they, sometimes or maybe assume things are linear or whatever. And so they said, well, maybe we can use a kind of reinforcement learning, deep learning, enhanced version of a control system. But in order to do that, they didn't want to just like run this tokamak a bunch of times. They trained it on simulations. So they have simulations of what the plasma looks like. They trained this model on that, and then once they had a super duper fast emulator of what would happen with the plasma, then they were able to stick that together and make a very good control system. And so that's also, I think, super exciting, and they've achieved like really impressive results in terms of their ability to confine this plasma. So looking at that particular example and going back to kind of what I was talking about earlier, just kind of recognize that fast AI machine learning emulators of classical numerical simulations enables these systems to be able to be embedded in either like a decision-making or control or like design loop in places where that was previously infeasible. And so I just gave several examples, and this is somewhat connected to when people are talking about the world models and how AI has this possibility of using AI as a world model. That fits together very nicely with classical engineering ideas of model predictive control or model-based reinforcement learning and those kinds of things. And so this is going to be the first of what a series of patterns that I'm going to try to name. And so this is what I'm just basically using AI and ML to enable decisions, control, and design. So that's the capability that you got with AI was to be able to make really fast emulators, and what that enabled was the use of AI in those settings. But that, that observation is great, but it's not representative of everything that's going on. So while AI is clearly like raising the ambitions of scientists, the capabilities that it enables varies significantly across the different fields, and so I want to kind of explore some of those other ones. So let's think about the use of machine learning in the context of molecules, materials, and mathematics. Like those are not grouped together at all in terms of, like you would probably not normally put together molecules, materials, and mathematics. Right, and like when I talked about that dog stool workshop, the way that we were organizing the research was not like this. You would have never put them together. So what do they have in common? Well, this is an animation from David Baker's lab, who won the Nobel Prize in Chemistry last year for designing proteins. And what they are using is sort of generative AI type tools, but instead of making language or making images, they're trying to generate new proteins. So here's a novel protein that can bind to insulin. And so this is this is not an emulator. This is like a totally different kind of capability. And you see things like that happening in other places, for instance, in terms of materials design, where they're using generative AI techniques to try to generate candidate materials that they hope will have some property, right? And maybe I should just say here, just because it's an interesting analogy, when people talk about when you want to make a text-to-image generative model, you give it a prompt like make me an image of a teddy bear on a skateboard or something, so that you're conditioning on this prompt and it's generating something new, like an image. In this case, you're conditioning on an insulin receptor. Like here's insulin. That's like the prompt, insulin. And then you say generate me a new protein that's going to bind to it. So if you're not familiar with that kind of, like conceptually it's still generative AI, but it has nothing to do with languages or images or anything. So they're doing similar things in the context of materials, where you say, basically, I would like a material that has a certain property. Can you generate candidates, that might actually have that property? And but the thing that's kind of interesting about this is that if it was a new drug or something, you wouldn't take this AI dreamed up drug and like inject it to your body, right? You want to know that it's safe, and you also want to know that it's actually effective. Like, does it actually have the property that the AI model thinks it does? Similarly, if the material, you want to make some new material that you hope has some property, Well, there's no guarantee that it does, right? So you could worry, well, okay, well, I don't have any guarantees from this AI system, but there's another way of looking at it where you don't really care. You're going to test it in a lab, right? You're going to you're going to synthesize it and check its properties. And in that sense, the AI doesn't need to be like provably correct, as long as it's accelerating the discovery process and you still have a good way of confirming that it has the properties that you want, right? So that's quite different than other kinds of models. And I think when you hear about AI in science, this is probably the bulk of where a lot of the activity is right now, partially because there's a lot of money in these areas. What might be a little bit surprising is it's basically the same pattern that's happening in mathematics. In mathematics, you want to say prove a theorem. It's hard to, I don't know, there's like a lot of candidate solutions for how you prove this theorem. You could just ask a bunch of people to write down a bunch of guesses, but there are now systems that are formal systems where you can formally verify if a certain candidate proof actually proves a theorem. And so you have an ability to verify a candidate solution in the same way that you're verifying if a material or a drug has a particular property. And in both cases, you're using generative AI to accelerate that search. So that is the second pattern that I would name, is this idea of exploration with confirmation. So you're using generative AI to explore this very complicated design space, but you still need to be able to have some external thing that is not AI to confirm or verify those potential solutions. Okay, now those two examples are also wildly different than the way that we're using AI and machine learning, for instance, in particle physics or in cosmology or astronomy. In those situations, you have a kind of an experimental device like a particle collection that's collecting data, and then you have some complicated workflow where some data analysis pipeline where machine learning or AI might be pieces of that. But then the goal of that data analysis pipeline is not to just spit out random candidate solutions. I mean, you're analyzing the data and you're going to like write out a scientific statement like, we measured, the mass of the Higgs boson to be whatever plus or minus something, or we discovered a new particle, or something along those lines. So this kind of model, like this kind of pipeline, is very, very different. And in those cases, like mistakes really matter. Being able to do uncertainty quantification really matters, and so you have a different set of challenges. So that's another pattern, is the use of AI machine learning for kind of data analysis and inference. So I'll say a little bit about simulation-based inference here. This is like what was alluded to in my introduction. And when I talked about simulators at the beginning, I talked about how they're maybe good at generating synthetic data, but they're hard to use for statistical inference. This is basically what the challenge that I had in mind. So the statistical framing here usually is that, like, on the left over here is basically your theory. And your theory has some parameters, and I'm using that symbol theta to describe the parameters of your theory. And then on the right, you have the data. And I'm using the symbol X to describe your data. And going from left to right, from the theory to the data, is making a prediction. And it's kind of a forward model, or your simulation of what you think is gonna happen. And the other thing that we do as scientists all the time, we make predictions, and the other thing we do is inference. So from the data, we would like to infer something about our theory. So that's this inverse problem. Now, there are different kinds of simulators. Some of them are deterministic type simulators where you put in some initial conditions and they evolve with time according to some specific rules, like fluid mechanics or something. And others are intrinsically stochastic. And so that includes things like, for instance, agent-based models, or like things that involve quantum mechanics and stuff like that. And so here's a simulator at the top where you see the balls that are bouncing around. And then the balls land somewhere in the bottom. And so in this situation, the idea is like where they land is supposed to be kind of the thing that you observe, and the path that they took to get there is kind of too complicated. I didn't either get to see it, or I wasn't paying enough attention, or I don't have like a good enough way to sense that. So those unobserved kinds of random variables are what people often refer to as latent variables. So if you want to know what's the probability that you land in one of those bins, you would need to kind of add up the probability of every possible path that might get you there and their probability, and that kind of sum or integral is usually totally intractable to do. And because of that, the probability of the data given the parameters, which is often referred to as the likelihood function, is intractable. And so that is kind of the core reason why simulators are they have a mechanism inside, like the ball's bouncing around, but they're difficult to use for statistical inference because their likelihood is intractable. So it motivates an entire class of inference methods where you can forward simulate, but you don't know what the likelihood function is, and that's a very general setting, and it applies to both like Bayesian and frequentist types of approaches. Because of time, I'll be a little bit quick here, but that's been a lot of the work that we did in simulation-based inference. So the high-level cartoon of what's going on is that you have your simulator, and you can run it a bunch of times, and you give to a neural network both the output, the synthetic observations X, as well as the values of the parameters that you use to run the simulator. And machine learning is really good at kind of learning patterns, right? So it ends up being able to learn essentially the statistical relationship between the observed data and the parameters in a way that you can effectively basically approximate the likelihood function. And then once you do that, you can do statistical inference in kind of the normal way. So that's been very exciting for a number of different areas. And so in a particle physics context, maybe I'll be quick with this example because of time, but in a particle physics example, you have some theoretical parameters of, how particles interact. Maybe you've seen these kinds of diagrams, the Feynman diagrams, these ideas that these lines are supposed to be particles either coming into a collision or going out of the collision. You can, that diagram is kind of a visualization of a calculation that you can do. And then once those particles are produced, they will maybe radiate a bunch more particles, and there's a different type of physics at play there with a different group of physicists that model those kinds of phenomena. And then those particles then hit our big, huge detectors, and they like ionize particles inside the detector and do all sorts of things. We don't get to observe all of that stuff. All of those kind of randomness that's happening is happening either at some microscopic scale or some scale that we don't have instrumentation to observe. And then finally, we get to the observed data. And we have simulations for each of those, the phenomena at each of those different scales. And so we can sample from them. So we can effectively do this sampling. And what that simulation chain conceptually is describing is this, this likelihood function, which is what we kind of ultimately want to know. And conceptually, it's doing this massive integral, but you're never going to actually do this integral. And because of that, the likelihood is intractable, and so that's the problem. So in a particle physics setup, this plot on here is like two parameters that we want to measure. And the big red ellipse is a traditional approach to trying to measure them. A tighter ellipse means a more precise measurement, right? And with these kind of simulation-based inference approaches, we're able to go from the red ellipse to this blue ellipse, and that might not look like wildly, amazing, but this corresponds to like many orders of magnitude more data at the Large Hadron Collider, and that's like, billions of dollar experiment. So these types of advances are like definitely something that the field is quite excited about. But this is also happening in gravitational waves, these kinds of techniques. It's also happening in, for instance, here's an example, singular molecule force spectroscopy. And it's happening just all over the place. So we've made a website recently that's kind of automatically going through the literature to find out what's going on. And you see papers here and let's see, education, economics, neuroscience, quantitative biology, astronomy, finance, genetics, epidemiology, medicine. So this abstraction has turned out to be incredibly powerful and is like I think pretty exciting, but again, it's like one of many patterns about how AI is accelerating science. Okay, so in my last few minutes, I want to talk about some other patterns that are a little bit higher level and kind of bigger picture about like the last two at least are bigger picture. And so these patterns actually come from a paper by Mario Kren and company called On Scientific Understanding with Artificial Intelligence. And I'm going to read the abstract of this paper, the opening paragraphs, because I like it a lot. It says, imagine an oracle that correctly predicts the outcome of every particle physics experiment, the product of every chemical reaction, or the function of every protein. Such an oracle would revolutionize science and technology as we know them. However, as scientists, we would not be satisfied with the oracle itself. We want more. And I think that's kind of interesting because there's a sense in which AI might allow us to do all sorts of stuff. It was kind of maybe it's like this oracle, but it's somehow still unsatisfying, right? So we want to comprehend how the oracle conceived of these predictions. And this feat, denoted scientific understanding, has frequently been recognized as the essential aim of science. So I think that that's kind of an interesting, somewhat metaphysical question about like, what are we trying to do here? And I agree with that a lot. So up until now, the AI has been basically a tool that allows you to gives you some capability to do something that you weren't able to do before. Of these three examples, the first one that they called a computational microscope is basically another one of those. And then the last two start to be more human. So let me tell you a little bit about this computational microscope one. And I'll be kind of fast here for time. So in this example, I'm going to take you deep inside of an atom. So you have an atom, and it has a nucleus, and the nucleus has protons and neutrons. And then if you happen to know it, those protons and neutrons are even made out of smaller things called quarks and gluons. And we have a fundamental theory that describes how those quarks and gluons interact to make the nucleus happen. And we call that theory quantum chromodynamics, or just QCD, okay? And and in that, you get various kinds of emergent phenomena, all sorts of interesting things happen. And on one side, we kind of know the equations. Like literally, these are the equations, you have to know how to read them, but that describe QCD. It's very concise. But actually making predictions with it is very, very hard. And so the way that we usually do that is through a computational approach, where you just imagine space and you like literally make a grid in space, and you also do time. So it's like a 4-dimensional grid, and then you have these quantum mechanical fields, and they're jiggling around like in that animation there, and you can numerically describe that thing, and you can use that to make predictions. And in this approach of doing it, you don't just have one movie, you have to imagine an ensemble of like all the different ways this quantum mechanical field could jiggle around. And so that's kind of like the series of different images there. And so you need to sample these incredibly big, they're like sampling movies, right? You have to have, here's a movie of what might have happened, here's another movie of what might have happened, and I need to sample a bunch of those with the right proportions. And that's an incredibly hard computational sampling problem. And for those that are experts, this is what Markov chain Monte Carlo was invented for. And so this approach works pretty well, but at some point it kind of runs into a wall. And so what we've been doing recently is thinking about, can we use generative AI approaches to accelerate this? And so generative AI is also good at making a bunch of examples. So you show it some movies, essentially. You train it on that model, and then you try to generate more and more movies. But in this situation, you still need to be able to maintain some kind of exactness guarantee. So it's not like the accelerate, it's not like the kind of explore and confirm. You need to sample. It's not going to be perfect, but you need to understand how to correct for that to be able to make sure you get the right answer. So we partnered with DeepMind and MIT to do some things in this space, and it's been pretty exciting and interesting. I'm not going to go into the details, but an interesting thing is essentially the same idea happened in the context of molecules, where you have, instead of sampling quantum mechanical fields, you want to sample different configurations of some protein. And so, for instance, in that figure, there's two examples of two conformations of a protein, and one of them is maybe more stable than the other. One of them might be metastable and might be a drug. And you want to know, like, what's the shelf life of this drug? So you need to know how stable that thing is. And that's basically the same statistical mechanics problem as our quantum field theory problem. And in both cases, we're using generative AI to try to accelerate that sampling process and to be able to answer some questions that were previously inaccessible. Okay, so I have about 5 minutes to wrap up and then leave time for, I see that I have 38 minutes that I started, so I think I'm still pretty good on time. But so I'm gonna talk about these last two, this resource of inspiration and kind of an agent of understanding, which are a little bit more humanistic. And so again, I'm gonna start with the particle physics one, and if it doesn't seem accessible, that's fine, because it's in some sense kind of the point. So I was working with some colleagues that do like kind of very mathematical theoretical physics, which is beyond my pay grade. And they are doing a lot of these kinds of calculations where you see these sorts of diagrams appear all the time. And they use that to try to calculate basically the probability of what happens when some particles scatter into each other. And the approach that's been used to do that has worked well for a long time, but it's hitting scalability issues. And so we started thinking about, could we use generative AI in that setting? And I won't go through all of this, but basically there's some equations, and we essentially just need to figure out the coefficients that go in front of a bunch of terms. And for reasons that I'm not going to explain, they have to be integers. So I have a bunch of letters, and I have some integers. It's a very discrete type of problem, and we realize it looks a lot like language. So we're using language models, but not like English language models. It's just the same architecture with our made-up mathematical language. And we're giving them a bunch of data from previous calculations, and we're trying to ask these models, can you guess what the solution to this problem is? And for those of you that might know some things about like cryptography or NP-complete problems, there's a class of problems where the solution is incredibly hard to find. Like it'd take an age of the universe to find the solution, but confirming that solution is fairly easy. So this problem fits into that category. So we are trying to use the AI model, just like before, in this kind of exploration with confirmation to guess the answer. And if we can guess the answer, we can confirm it. And we have been making good progress there. So we have these models that are like 99% accurate in guessing like what the coefficient should be. And we're on the verge of being able to solve a really hard theoretical physics problem. So that's exciting. But in the process of doing it, we started to realize that there's some kind of what we would, like if we did it, if we were successful, it would just look like a numerical thing. It would be the oracle that guessed the solution without us having any idea of like why the solution is what it is. And so our problem is, in some sense, like these kinds of problems that you get on an IQ test or something. Like here's a sequence of numbers, like complete the sequence, right? And for those that know, this is like the Fibonacci sequence, and so you know how to complete it, but it's not really enough information. You could imagine there's lots of possible answers to that. And maybe here's another one that you've seen, Pascal's triangle, where there's some pattern, and it's kind of like, you don't know what the pattern is, but if you kind of try to figure out what is the pattern so that you can extend the triangle and keep going. Our problem is sort of like that. But in both of these equations, the answer is expressible as a simple rule. So we're looking, can we discover what that simple rule is? And in the process of doing this, like ours is like that, but it's like a 6-dimensional version of Pascal's triangle. We have found answers. And I'm not trying to read these, but the point is that we have used AI type techniques to actually discover equations that describe what is the simple rule. And in some cases, before the AI found it, we found it as humans. But the way that we found it as humans, we would have never gone there kind of if we weren't trying to like work with the AI systems to get there. So that version of the kind of working with AI to try to go back and forth, sometimes there's this kind of notion of AI being a resource of inspiration. And there are many examples in mathematics where things have been proven, counterexamples have been found, where the human alone, didn't do it, but the AI didn't do it, but the two together kind of worked together, and then the humans kind of finally figured it out and then was able to go to that next stage. So that's this resource of inspiration model. And the last one, I'll just say, and I'll conclude with this, is this idea that now that we have kind of more and more powerful AI, we're asking ourselves this question of, could AI ever kind of start to do the science autonomously, and what would that mean? And what would that mean for like humans' role in doing science? And when we think about that, you really have to go and think about the bigger scientific loop and thinking about not just doing inference with data, but actually designing experiments or generating hypotheses and that entire loop. And I know that there was some talk about that earlier with, for instance, the Microsoft Discovery platform and various papers. There's a quote, a tweet from yesterday by Sam Altman pointing to Future House's work. This is a super active area. I think that while there's some compelling stuff that's there, I think most of them are happening in relatively narrow spaces. And what you mean by science is still relatively narrow, but it's moving very, very quickly. And there are some deep questions there. And so I'll end with this quote from Freeman Dyson. He says that new directions in science are launched by new tools much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways, and the effect of a tool-driven revolution is to discover new things that have yet to be explained. And I like this quote a lot, and I used to use it to make the point that AI is essentially a tool that's allowing us to, hopefully find some new physics. But what's going on in that last slide about kind of autonomously discovering things and generating hypotheses is also really kind of a concept-driven revolution. So I think in some sense we're experiencing both of these simultaneously, but they're not really the same. They're two different threads that are happening kind of on top of each other. So with that, I will end. Thank you very much.
So we have some time for questions. How much time do we have? Fantastic. So some excellent questions have been put up here. I encourage you to continue to ask questions. They show up here almost immediately. So, and also if you have a question you'd like to do the more traditional thing here, there's a microphone. But to sort of kick things off, what would you say are the prospects for a fully general simulation-based inference technology, which would be, I guess, agnostic as to the simulation model and to the nature of the data?
Yeah, so that's a great question. I think that in some sense there are already toolkits that are out there that are very generic for doing simulation-based inference, where you just kind of, you have a simulator, doesn't need to know any details about it. The problem, and so in some sense that exists. The problem is that it only kind of works for if, or it will start to fail in various ways. So if the dimensionality of your data is incredibly high, then you need a lot of simulations to be able to train the model to do what it is that, to learn the things that you need to learn. And if your simulator is expensive, you might not be able to generate enough data for that to be successful. Similarly, if the dimensionality of the parameter vector that you want to infer is very high, similar problems. And so that depends a little bit if you want to set things up as a Bayesian or a frequentist, or like which problem you'll run into first. And so I think there will always be some kind of, frontier of where the problem, like where the methodology allows you to go, and that's driven largely by how sample efficient the algorithms are. But there is an opportunity also to not treat the simulator as a black box, but to kind of reach inside of the simulator and make it somewhat of a gray box simulator. And if you have access to certain information, like sometimes you can calculate a gradient, or sometimes you can calculate some other, probability of something that's happening inside that you can expose, and then you can incorporate that in the training of these machine learning models. And we have examples where we were able to reduce the amount of simulations by like 5 orders of magnitude. So like, dramatic improvements in efficiency. But that's tailored to that problem. And I don't think that's gonna go away. I think that from a fundamental perspective, these are hard problems. And if you wanna have it work efficiently, you're gonna have to leverage something about the nature of your problem. And for right now, humans are in charge of that. In the future, you could imagine some AI model that can introspect the simulator and figure out what trick to play, but we're very far away from that.
So actually, the highest ranked question right now is sort of follow-up to that. So it says, in your opinion, will AI be able to observe the world and identify and prioritize problems to solve, or will we always have to input variables for it to solve and build upon?
Yeah, no, that's a great question. I had to go a little bit quick at the end, but maybe I'll go back to this figure, is that and this is related, I think, to probably anticipating a lot of the kinds of questions and in terms of like, if you wanted to start to automate science or have an autonomous scientific agent, oftentimes you sort of imagine like, we're just gonna completely break from the past and replace it with this new automated scientist thing. And I think it's very hard to have a useful conversation about that because it's so vague. If you start thinking about the pathway in which you would start to replace individual pieces, it's a more grounded discussion. So at the beginning, if you just said, I have a theory, I can express my theory as a simulator, and I'm gonna collect some data and I wanna do inference, how do I do that in an automated way? We didn't really know how to do that, and I'd say that like roughly simulation-based inference is kind of like, that's how you can do that. But now you wanna say, start to design what experiment should you do next, right? If you wanna do that, if you have a very tight experimental protocol, it's essentially another optimization problem. You kind of go through all the experiments you might do, and there's different ways you can set it up, but you can basically think of it as like, which experiment am I gonna learn the most from in some formal expected information gain system or something like that. And then it's just a question of how do you do that efficiently? And, but it's kind of clear enough. But if you wanted to start to work with more open world models of like what kinds of experiments might you do, then it becomes much, much harder. And humans are very good at that. We're not like just scanning through some experimental protocol. We're like thinking about entirely new kinds of experiments. And that's really not clear how you do that right now. I do think that what's going on with language models and things is starting to be, something that would maybe have those kinds of capabilities, but we're still pretty far away from it. But the other part is that when you design those experiments, you're not simulating what might happen for every possible scenario, right? We work at a much higher level. We reason about these are the kinds of phenomena, they would probably give rise to this kind of thing and this kind of experiment, and you just think at that level about what kind of experiment would be useful. So we would also need AI type models that can do this reason at a higher level if you ever wanted to be kind of, even remotely efficient. And we're not very far along in terms of having AI models that can work across different levels of abstraction like that. And so as long as humans are in charge of doing that, which we basically are now, then it's really important that we can inspect what these AI models are doing, right? So like one narrow notion of interpretability is that if I do an experiment and I see something weird, I need to think about how does that influence my hypothesis generation for the next experiment I should do, and what the design of the experiments that might be useful for telling this hypothesis from that. And if we can't inspect the models, then we're not effective at doing that. In the future, maybe AI models will be able to introspect themselves and do it, but I think it will still be important that they have some kind of notion of causality and some kind of ontology, and we're pretty far away from that.
Quite aside from the utility of human intervention, it's also more fun.
Yes, absolutely, yeah.
So another question. This one is just asking for some elaboration on a point that you made in passing, sort of towards the beginning of your talk. So could you elaborate on the point that a prompt, I think this was in the context of the insulin example, yes. That a prompt to effectively an AI might not involve language at all? Right.
Yeah, I mean, it's well, I guess maybe here's one way of saying it is that if you train, when you do these like text-to-image type models, when you train them, you give it a bunch of, at the beginning you have to say like, here's a bunch of images, here's a bunch of examples of text, but then you need to somehow relate those two. And so a common way to do that is, for instance, if you have a bunch of image captions, then you know that the caption and the image kind of are related in some way. And so then when you have like machine learning models that ingest either an image or they ingest text, they try to make it so that the kind of abstract representation that comes out of these things are close by. So they have like the shared abstract representation for different types of data modalities. But you can do that for basically, it doesn't have to be text and images. It could be any paired, any sets of things that you want. So for instance, in multimodal astronomy, you might have a telescope that's observing the universe and optical, and another telescope that's looking at the universe through X-rays or something. And the data might look very different, but you could say, I want you to have a kind of a shared representation for them. And that idea applies to sort of any kinds of data modalities you want. And so once you are able to work with different kinds of data modalities, then there's a part where you're like, okay, I want you to generate me one kind of data conditioned on another kind of data. And so instead of conditioned on a text prompt, make me an image, you could certainly do the other thing around. You could say, here's an image, generate me a caption, right? But you could also say, here's an image, generate me a song, or what have you. And so that applies in the scientific settings as well.
I think as you were pointing out towards the end of your talk, the process of actually working that out sometimes leads to conceptual simplifications.
Absolutely, yeah.
So one more question. We still doing good for time? Okay, so this question asks, what are the current limitations for the continued advancement of AI in the context that you're describing it, machine learning and AI? Is it computational capacity, hardware materials, I guess this is a meta question. Is AI being used to solve these problems themselves?
Yeah, I mean, it's a good question. I think, without trying to sound like I'm avoiding it, I don't think there's like a uniform answer to that. And so I think part of the motivation for presenting these different patterns for AI and science, or there's other discussions about kind of the taxonomy of all of the activity in AI for science, is that the answers to questions like that, like where is the bottleneck, or what's stopping you from advancing, or where is the opportunity, is gonna look different in those different contexts. But there can be something shared about them. So I think for the things that fit in a particular pattern, the bottlenecks are generally kind of aligned. So in the context of this, data analysis simulation-based inference, one of the bottlenecks is essentially how many simulations can you make? And so that's generally the bottleneck, right? And then in other cases, like the confirmation with discovery, it's essentially like how efficiently can you do this loop? And how efficient is your loop between here's a candidate solution, and can you check that it has that property, and then feed that back into the system to kind of refine it. And so each of the problems has a different bottleneck, and that's, I think, part of the point of talking about these patterns, is hopefully it helps us navigate that more efficiently.
Fantastic. Okay, so I guess we have time for one more, so let's see here. Trying to find one that's not too much navel gazing. Here we go. So this might open a can of worms, but can an AI model quantify the uncertainty in its predictions to guide researchers on when to rely on the model and when to conduct further experiments or high accuracy calculations?
Yeah, so that's a great question. So I think that, in some sense, there's different levels of that too, but a lot of AI approaches at first were like, here's an image, is it a cat or a dog or something? And they were like kind of predictive models, and they just gave you like an answer. You might say like a point estimate or something. And then sometimes there was some notion of a confidence score, but those are usually terribly calibrated. So like, I think it's a dog with 99.9%, and that's not definitely, that makes mistakes more often than that. So there's a notion of like, how can you do uncertainty quantification there? But the simulation-based inference thing is like natively about uncertainty quantification. The thing that you are trying to communicate is a probabilistic statement, and you're getting confidence intervals or posterior distributions. So that's one of the reasons I think it's exciting, is because it's like squarely aimed at uncertainty quantification in the way that scientists would normally talk about uncertainty quantification. Then there's a higher level version of like, okay, well, what if my simulator's wrong? Well, if your simulator's wrong, you will have problems, and that's real. And so how can you be robust to those kinds of mismodeling effects, and what statisticians would refer to as model misspecification? But that's becomes a very grounded question, and you can make some progress in that. And one final thing there is all those fundamental questions don't really have anything to do with AI. Like, they're fundamental questions that like statisticians and people have been asking for a long time. They maybe manifest a little different once AI is in the mix, but the foundational questions haven't changed. Yeah.
That's right. Fantastic.
Great.
Thanks. Let's thank our speaker one more time.
Thank you.